Hey, this is Horner. We're going to look at problem number 1 in chapter 1. It says the gardener is told that he must increase the height of his fences 37%. So if we want to do that to keep the deer from jumping over the foliage, I would start just by saying, well, we know our original fence was 100%. We need that additional 37%. So our new fences have to be 137% the height of the old fences. So let's just take that 137%. We're going to divide it by 100. That'll get rid of the percentage itself, and we end up with 1.37. So that's our factor that we're going to multiply by. We're going to take 1.8. That's the height of the original fence, and we need to multiply that times our factor, which is 1.37. So our new fence needs to be 2.5 meters high. For number 2, actually this is not number 2, it's going to be number 6. So for number 6, Samantha is 1.5 meters tall on her 11th birthday and 1.65 meters tall on her 12th. They want to know by what factor has her height increased, and then they want to know what is the percentage then. So in order to do the factor, that's the first part, we're just going to take 1.65. That is her latest height, and we're going to divide it by her height that she had originally, which is 1.50. You'll notice that the meters do cancel, and when you divide those two things, you'll get 1.10, and that would be our factor. So to find the percentage here, what we'll do is we'll say we take our factor, 1.10, and we subtract off the value of 1, which would be 100%, and that gives us with 0.10. Which then, if we multiply by 100%, so times 100%, would give us an increase in height of 10%. And that is number 6. Let's go ahead and take a look at the next one, which would be number 13. Number 13 says, in cleaning out the artery of a patient, you've got a doctor who increases the radius of the opening by a factor of 2. They want to know by what factor does the cross-sectional area then of that change. So to do that, we know that we're just going to say that the cross-sectional area here is equal to the area of a circle, which is pi r squared. So if we think about the inside of that artery, it looks kind of like a circle, so we're going to just approximate it. It does have a radius out to here, and so our area would be pi r squared. Let's go ahead and start this. We know that the first area is equal to pi times the first radius squared, and we know that the new area would be equal to pi times the second radius squared. We're going to rewrite A2 now in terms of what we had for A1, knowing that our factor of A2 is 2 times that of A1. So here we're going to say A2 is equal to pi, and then now we've doubled the radius, so we're going to do 2 times the original radius, and that's what R2 is. So basically here we could say R2 is equal to 2 times R1. And now that we've got 2 times R1, we're going to square that, and now we've got 4 times pi times R1 squared. To form our proportion, we'll just say A2 over A1 is equal to 4 pi R1 squared all over pi times R1 squared. And that, when you're done, if you just cross these off, since they're the same, we end up with a value of 4. So the cross-sectional area of the artery does increase by a factor of 4. The next part should be relatively easy for you to do. This is number 18, letter A, and all they want you to do in this one is to rewrite some numbers in scientific notation. So if we have 310 million people, if I want to write this in scientific notation, remember the unit is really important. You'll notice that I'm going to go back 3, 6, 7, 8 to the left. I'm going to go 8 places to the left, so I'm going to put 3.1 times 10 to the, and then that 8 tells us how many places we moved people. So much easier to recognize this number than it is the larger number, and less prone to having us make mistakes. Letter B, for the second one, we've got a really small measurement. It's 0.0000000000000, and then 0038. So we need to count how many times did we move to the right. So 3, 6, 9, 12, 13, 14, and then we need to put our decimal point just to the right of the non-zero number there. So this would be 3.8 times 10 to the negative 15th meters, because our original number was this. So much easier to say 3.8 times 10 to the negative 15th than 0.00000 and all the way over to the 38 there. So it makes it a lot easier to do. For number 20, there's several parts to number 20, so let's go ahead and take a look at part letter A. So 20, and then this will be part A. For 20 part A, all we're doing here is going through and writing our answer to some problems with the appropriate number of significant figures. To do this one then, we've got, this one's just addition, so we've got 6.85 times 10 to the negative 5th meters, and we're adding to that 2.7 times 10 to the negative 7th meters. We need to get these with the same exponents in order to really see which one has the fewest numbers to the right of that digit. So let's do that. We're going to write 6.85 times 10 to the negative 5th. We're going to leave that one the way it is, and we're going to change this one to times 10 to the negative 5th. So to do that, we've got to make this number 0.027 times 10 to the negative 5th meters. Now that they have the same coefficient here, we can add the two together, and when we add them, notice that the number that is the closest to the decimal to the right would be this number, so that's where I'm going to need to round. This one has the number that you could round to if it was just it is right there, but here we're going to round it to the hundreds place instead of the thousands place. So you go ahead and add these together. So we're going to do 6.877 times 10 to the negative 5th meters. But because we said we need to round to the place closest to the decimal, to the right of the decimal, with the number that has the smallest number of numbers to the right of the decimal, I know that's really wordy, we're going to need to round to here. 7 is going to round up because we've got a number that is greater than 5 there, so this will be 6.88 times 10 to the negative 5th meters. So that's letter A. Let's do the same thing with B. I've got another addition problem. So we've got 702.35 kilometers, and we're going to add that to 1897.648 kilometers. So remember, in addition subtraction, we're looking for the number that has the fewest number or the fewest digits past the decimal point. So that would be this place right here, and that's where I want to round it to. When I add the two together, I'm going to go ahead and put my 8 here. 5 and 4 is 9. 6 plus 3 is also going to be 9. 7 plus 2 is 9. And then I've got a 9 here. You kind of see what's happening. 8 and 7 is going to be 15, so this is going to be 2599.998. When I add these together, this is what I get, but I want to round to this place. So that's what I'm going to do. All my 9s here are going to move up, so I'm going to get 2600, but I still want to make sure I go all the way out to this hundreds place. So I'm going to have 0, 0. It's really important that I have these two zeros, or because in this problem I'm going to have 1, 2, 3, 4, 5, 6 significant figures, and if I just had this number 2600, only have 2 significant figures because there's no decimal point here. So be very careful with what you're doing. And that would be kilometers. It's because we added the 2, and then from this step to this step, we just found out how many significant figures it has. So that is 20B. Let's go ahead and take a look at the next one, which is 20C. For 20C, we're going to take 5 meters. So this is 20 part C. We have 5.0 meters, and we're going to multiply that times 4.3 meters. When I go through and do this one, I'm going to end up with 3 times 0 is 0, 5 times 3 is going to be 15. Then I've got 0 here, and 5 times 4 is 20. So I end up with 21.5 0.50 meters, but I can only have as many significant digits as I have in the number with the smallest number of significant digits now, because we are doing multiplication. This one's got 2 sig figs, this one's got 2 sig figs, so my final answer here can only have 2 significant figures, and so this is going to be 22 meters, because the 21.5 will round up to be 22 since I have 5 here. If it was 21.4, we'd just leave it at 21. So that is 20C. Go ahead and move on to letter D. For letter D, this one's a little tricky because they've given us 0.04 and then they're dividing it by a number that has an infinite number of significant figures. So we're only going to go by the number that we have on top. So this 0.04, and remember this is all centimeters here, 0.04 divided by pi. 0.04 only has one significant digit. This 0 is just a placeholder. If we made this in scientific notation, it would be 4 times 10 to the negative 2. So we're going to take 0.04 divided by divided by pi, and we're going to end up with 0.01 centimeters. This one only has one significant figure. For letter E, we're going to have 0.040 divided by pi. So notice what we've done here is we've added this 0. It is a significant 0. This one is important, but it is also non-significant. It's important because it holds the place, but it's not a significant value. We didn't measure out to this 0. Instead, we measured out to this 0. When I divide those two, I will get 0.013 as my answer, and we're going to put that in meters. So we rounded this one to 1 sig fig, we rounded this one to 2 significant figures, and that is the end of number 21. Let's go ahead and move on over to number 22. In 22, they just wanted us to find the number of significant figures in each number. So 22, letter A, is super easy. It's 7.68, so then that one has 3 significant figures. For letter B, the 0.420, in fact they put a 0 in front of it too. This one has 3 significant figures also. This number is important because it just shows us it's in front of the decimal, but it is not significant. The number after the decimal is significant, so that is a significant figure. So there are 3 here. The non-zero numbers are also significant figures. For letter C, we've got 0.073 meters. This one only has 2 significant figures. Remember, leading zeros, as long as there's not a non-zero number here, leading zeros, even with the decimal, are not significant. They are important because they tell us the magnitude of the number, but the only numbers here that are significant are the non-zero numbers after the decimal, and if I had another 0 here, it would be significant because it's after the decimal after some numbers, but this one's only got 2 sig figs. For letter D, this number is 7.68 times 10 to the 5th, and our unit here is grams. This one has 3 significant figures because we ignore the times 10 to the 5th. That just tells us it's a placeholder kind of where all the zeros might be if we had them. So this one is 7.68, so there are 1, 2, 3 significant figures in it. For letter E, 4.20 times 10 to the 3rd kilograms. This one also has 3 significant figures because even though this 0 is after the decimal, it's after a non-zero number, which is different than this 0. This 0 is not after a non-zero number. It's got a 0 before it, so it is not significant. This one is significant. This one is not. So significant figure here at the end, and we end up with 3. And that is number 22E. For 22F, we have the number 7.3 times 10 to the negative 2nd meters, and so this one does have 2 significant figures. That one's pretty easy. And then letter G, we have 2.300 times 10 to the 4th seconds, and so all of these digits are going to be significant because both of the zeros come after a non-zero number after a decimal. And that's how we can tell that these two are significant. We actually measured all the way out to this 10,000ths place. And that is number 22. Let's go ahead and take a look at number 26. Number 26 has to do with units. It wants us to convert each length to scientific notation. To do that first, for 26a, we've got 1, and then this is micrometers. A micro is basically just 10 to the negative sixth, so our answer here would just be 1 times 10 to the negative sixth meters. So that micro means times 10 to the negative sixth. For letter B, this is 1,000 nanometers. Nano here just means times 10 to the negative ninth, so we're going to do 1,000 times 10 to the negative ninth. And at this point, we're not in standard scientific notation, so we need to move the decimal point 1 to 3 more places to the left, which then means that we can make this number go towards the positive. So here I'm getting more positive when I go this way, so I'm actually going to take negative 9 plus 3, and I get 1 times 10 to the negative sixth meters again. So you'll notice that 1,000 nanometers and 1 micrometer are both exactly 1 times 10 to the sixth meters. For letter C, I have 100,000, and then PM is picometers. This would be 100,000 times 10 to the negative 12th is what pico means. Now I can go ahead and 12, 11, 10, 9, 8, 7. So this is really 1 times 10 to the negative 7th meters. For letter D, I have 0.01 centimeters. That's equal to 0.01 times 10 to the negative 2, which then will give me 1 times 10 to the negative 4th meters. And then finally we've got letter E, which they give us kind of irritating here, 0.000000, and then we've got 0.0001 kilometers. So that would be equal to 1 times 10 to the negative 10th. 1 times 10 to the negative 10th would be all of this, but then we still have kilometers, so we need to multiply that times 10 to the positive third meters, and that gives us 1 times 10 to the negative 7th meters. Last thing they want us to do in this problem is to rank these from smallest to largest. So I'm going to say that C is equal to E. So notice here's our answer for C, here's our answer for E, and then we would have A is equal to B, that would be the next biggest, and then finally letter D is our largest. And that one was number 26. Let's go ahead and take a look at number 28. For number 28, they want us to convert the density of body fat from grams per cubic centimeter to kilograms per cubic meter. So this is a little different. We're going to start, this is number 28 again, with 0.9 grams per cubic centimeter. And going from grams to kilograms is really easy to do. We're just going to draw our line here. We're going to say that there are 1,000 grams and 1 kilogram. That will get rid of the grams. But now we go to try to convert this centimeters cubed to meters cubed. I always start by just putting the raw conversion down. So 100 centimeters is equal to 1 meter. But at this point, I also need to recognize that I have cubic centimeters here. So I have to cube the centimeters, which means I have to cube the 100, cube the 1, and cube the meter. If you don't do this, you will not get the right answer. You'll be off by several factors of 10. I'm going to draw my double line. I now notice that I have kilograms on the top. That's my final unit on the top. And then my centimeters cubed go bye-bye, so I'm left with meter cubed on the bottom. If you do this math, you should end up with 900 kilograms per cubic meter. For the next problem, which is number 52, they want us to go through and estimate the number of times a human heart beats during its lifetime. So let's just say that the average human lasts for about 70 years. So that would be your lifespan. And let's say that your heart beats at 70 beats every minute. So beats every minute. Let's do 70 beats per 1 minute. And we also know that there are 70 years in a lifetime. So we're trying to figure out how many beats we'll have in a lifetime. We're going to go from, we want to know, we want to know how many there are in a lifetime. We've got to be a little bit careful here. We've got to get rid of the minutes. And so we also want to get rid of the years. We want to get rid of the minutes and the years so we have beats per lifetime. And we can do that very easily by putting minutes on the top. And then on the bottom, I can put 1 year. So I need to know how many minutes there are in a year. If you just Google it, you'll end up with 5.26 times 10 to the 5th minutes in a year. And now we can cross off minutes, we can cross off years, and we're left with beats in a lifetime. And if you do all that math, you should get something close to 2.6 times 10 to the 9th times, or beats per lifetime. That's a lot of heartbeats. Okay, so this one is number 55. This nurse went through and recorded a bunch of temperatures for a patient, and there's several things here that they want us to try to figure out for this patient. So the very first one is they want to know what is the temperature at noon. And so to find the temperature at noon, we can actually just go right to this point. In Logger Pro, if you use the inspection tool, you can actually go to that point. So right at noon, looks like time of day, they've got 11.5 there. I'm going to click right here at 12. So this would be at 12. So we need to figure out, oops, I guess this isn't there. We go. Now it's working a little bit better. So at about noon, it looks like that you're looking at a temperature of about 101.8. So you can see that down here in the bottom. You don't want to look up here necessarily. We'll get rid of that because that's just doing it to the nearest plotted point. But if we put it here, you'll notice down in the bottom, you see it's about 101.8 for 12 o'clock. The next part, they want us to estimate the slope of the line. What's really great about this program is it will automatically calculate that slope for you. But if you really needed to calculate it, it would be fairly simple to do. I'm going to switch screens here. Essentially all you would have to do is take 2 points on the line, and because all of our points are actually on the line, you'll see that there's no points above or below. We can even just use 2 of the points that we had. So 2 of the points that we had might be our slope here is just equal to the change in the values on the y-axis divided by the change in the values on the x-axis. And so we've got 102.6 minus 100. And we're going to divide that by 1 p.m. minus 10 a.m., which would give us 3 hours. And if we divide the two, you're going to end up with about 0.9 degrees Fahrenheit for every hour of time that passes. Let's go ahead and use the slope intercept form to figure out an equation for this, and then that will help us figure out in 12 hours, according to the trend, what this patient's temperature would be. And so here we're going to say y is equal to mx plus b, where m is our slope, and we said our slope was about 0.9. You can see the slope a little bit more exact here. The slope is in degree Fahrenheit for every hour. Since our time is in hours and our temperature is in degrees Fahrenheit, that's what we've got there. That would be our slope. Our x value is time, so we can just put in t for time, plus, and then we have our y-intercept, and our y-intercept here is 90.98 degrees Fahrenheit. So in the end, we could solve for y, and y here is really just our temperature. And you'll notice that the unit for temperature is an hour. The hours would cross off, and then we'd be adding just degree Fahrenheit and degree Fahrenheit. So here we could put in the 12 hours for our time. So let's go ahead and put in 0.9 times that 12 hours for our time plus 90.98 degrees Fahrenheit. And if you do your math, you're going to end up with 113 degrees Fahrenheit, and that would be bad. Our patient would not be doing well after that. So the patient would be dead before the temperature reached the level. So the answer to the question that they asked is absolutely not. And that is the end of number 55. For number 56, this is the last one that you had to do. This one says the patient's temperature was 97 at 8:05 a.m. and 101 at 12:05 p.m. So they say that the temperature change is linear throughout the day. They want to know what would the patient's temperature be at about 3:35 p.m. So let's go ahead and just find the slope for this. M would be equal to the change in temperature, and we're going to divide that by the change in time. Our change in temperature was about 101 minus 97, and we're going to divide that by the change in time, which is about 4 hours. So we're looking at about 1.0 degrees Fahrenheit for every hour of time that goes by. So let's go ahead and use our slope-intercept form for our equation. We know that the final temperature here is equal to the slope times the time plus the y-intercept, which would actually for us be the original temperature. Let's go and plug our numbers in. So that would be 1.0 degree Fahrenheit for every hour. That would be our M value. Our time value here would be 3.5 hours. So that's how long it took us to go from our 12:05 p.m. to our 3:35 p.m. And then our original temperature we know is 101 degrees Fahrenheit. If you go ahead and do your math, you should end up with 104.5 degrees Fahrenheit for that patient. And that is the end of the problem set for Chapter 1.